Kia ora koutou. My name is Tim Bell from the University of Canterbury in Christchurch, Aotearoa, New Zealand. Thanks for joining me as I share a few thoughts about teaching teachers about teaching computer science. Now, since we can't all get together here in New Zealand, I thought I'd film this talk in some locations around Ōtautahi, the city of Christchurch. So at least you can say that you've been to New Zealand for the conference, even if it's only virtually. But first, let's get some coffee. So, what has a cup of coffee got to do with teaching teachers? Well, in many countries, the situation is that few teachers have a computing background, especially primary school teachers. They may even feel like imposters, and that they couldn't possibly understand a session on a topic such as coding or computational thinking. So, we promise them a free barista coffee when they arrive, or a different drink if they prefer. To understand the importance of this cup of coffee, I want to introduce you to a word that gives us a deeper understanding of what it means to look after teachers beyond just giving them free stuff. It's a term that comes from Māori culture, the beautiful culture of the people who came to Aotearoa, New Zealand, long before my ancestors did. If you get the chance to visit us in Aotearoa, I hope it's something that you'll get to experience. The word is Manakitanga. A simplistic translation of Manakitanga would be hospitality, but it means a lot more than that. It's built on the word mana, which means honouring someone. It's about reverence and admiration. A person with mana is respected. Manakitanga is the act of showing respect and building up the mana of those who have come to spend time with you. Here, as in many cultures, providing food and drink is an obvious way to be respectful to a visitor, but Manakitanga goes way beyond that. It's about acknowledging who they are and what they do. I'm going to use this cup of coffee as an icon for Manakitanga. When we're working with teachers, we can acknowledge the care that they have put into hundreds, if not thousands, of young people's lives, their passion for giving vital life skills to their students, their experience in the classroom and in the school system, how they've probably given of themselves well beyond what they're paid for. We acknowledge that they've made the effort to be at the Professional Development Day, perhaps because they're keen, or perhaps they were told that they have to be there, or maybe they've just decided to take a risk and attend. With Manakitanga, we're also acknowledging that they have much of what's needed to teach computing. We know this because if an experienced programmer with no teaching background appears in front of a class, they often need a lot of guidance to make the occasion successful. Teachers already know a lot about classroom management, the education system, and how to make things happen in their school. Once we've got the teachers engaged, we need to build up their self-efficacy. When learning a new subject, it can take some time to feel part of the in crowd. In some countries, teachers are expected to have a degree in a subject before they can teach it. But with the sudden recent changes, this often isn't practical, and many teachers find themselves teaching computer science with very little support. Some management may even assume that it's easy and anyone can pick it up. We need to develop teachers' identity as a computer science teacher so that they build up confidence and don't just fall back to pointing students at the websites hoping for the best. Of course, sometimes there are also extremely enthusiastic teachers in the system. It's great having them to help others, but sometimes the enthusiasm needs to be tempered to avoid putting others off when they see a role model that they couldn't aspire to. If Manakitanga gets teachers on board, what do we then need to give them? Well, if we think about the TPAC model, as well as content knowledge, such as how to code, we need to think about pedagogical knowledge, ideas such as peer instruction, using Parsons problems, and providing them with resources appropriate for their classes. One easy way to do this is to model it as we spend time with them. Thinking about technological knowledge, sometimes teachers lack confidence using computer systems. And one thing we've found that works well in teacher professional development is using unplugged activities so that they have quick success in topics that they thought that they might have struggled with. There's growing evidence that students learn programming just as quickly if their lessons include unplugged activities, and it can even increase their self-efficacy. We think the same happens for teachers. Unplugged activities get them thinking. Working away from the computer removes the temptation to dive into coding without thinking first. And if we can build their self-efficacy, we're improving the chances that they will become engaged with this new subject. For example, a classic unplugged activity is the sorting network, in which each student starts off holding a number. They follow lines marked on the ground, and when students meet at a node, they compare the values they are holding, with the smaller one going to the left and the larger one to the right. In the end, all the students end up with the values that they are holding in sorted order. This can be a magical moment for the students. The magic is that a lot of very simple operations, in this case an if statement, can be combined in just the right way to achieve a complex outcome, sorting values into ascending order. In fact, this is the magic of computing, that there are just a few general operations that a computer can perform: reading input, storing values, following instructions in a sequence, selecting between options, iterating over a sequence of instructions, and giving output. So in just a few minutes, the sorting network exposes them to the power of computation. Of course, it means a lot more if they learn how to wield that power by learning to program, but experiencing this magic along the way is an encouragement to explore more and persevere beyond the syntax errors and bugs that may frustrate them in the learning process. And the same applies to teachers. Their time is precious, and this can help them to gain an insight into the power of computing in a short time. This explains why Unplugged is often featured in teacher professional development. But there's another effect it can have on teachers. Programming can conjure up images of trying to get new technology working, persuading IT providers to install something, and wasted lessons dealing with technical issues. An Unplugged activity uses familiar resources, in this case chalk, paper and pens, and maybe the odd reading book. So getting back to the TPAC model, working away from the technology can help to develop thinking that can then be applied on the computer. Another issue is that once teachers get into coding and start to see themselves teaching programming in the classroom, this can create the fear that they need to be able to debug any program that a student writes. This isn't the case. They need to be able to teach their students how to debug programs. Sure, it's helpful if teachers can find bugs, but it's way better if they're aware of strategies for debugging and asking the right questions, such as, what is this supposed to be doing, rather than robbing students of the opportunity to learn how to problem solve. We know from surveying our teachers that their biggest challenge is finding time to learn this new material. You can't just learn it all in an hour or even in a week's course. If it's worth putting in a curriculum over multiple years, there must be some substance to it. And successful school systems allow plenty of time for teachers to get up to speed. Some learning can happen on the job. I often feel as a teacher, I'm the best paid student in the class. But professional development does need some time away from the chalk face as well. And over coffee, so they can develop peer relationships and find other teachers in similar situations to themselves. In fact, they can build relationships while learning to program too. Peer programming for teachers seems to work well. Not only are they experiencing a useful mode of learning, but they get to feel what it's like for their students. Now, let's talk for a bit about language, the so-called jargon of computing, which some teachers see as scary language. There are words they may have seen in a curriculum document or heard about in the media, but they feel they couldn't explain themselves. I sometimes highlight what I call the ABC of scary words for teachers: algorithms, binary, and coding. And interestingly, these three words represent what computing is. An algorithm is brought to life as a program using coding, and the program processes data, numbers, words, images, sound, and more. But all that data is represented using nothing but binary digits. A number of times we've been asked for definitions of the words in the curriculum. This sounds entirely reasonable. Once you know what an algorithm is, perhaps you can teach based on the definition. But working from definitions is shallow. For example, how would you define a book? Well, I have a book here that has a definition of a book. It says that a book is a written or printed work consisting of pages glued or sewn together along one side and bound in covers. So this obviously meets the definition of a book. But is this a book? It meets the definition, but it's kind of a magazine. Or is this a book? It's really a newspaper, but it has covers and it's bound together with staples. Maybe this isn't a book. It folds out, but it's a map, it's a single piece of paper. There's a boundary there. And what about ebooks? Is that a kind of book? So we end up with complicated definitions. Yet a child who's never read a definition of a book could probably still tell you that one thing is a book and another thing is not a book. They can recognize them when they see them. Definitions leave us at the first level of Bloom's taxonomy. Knowing what something means is only the first step to using and applying the concept. And anyway, we probably can't even agree on what the correct definition is. According to Wikipedia, an algorithm is a finite sequence of well-defined computer implementable instructions, typically to solve a class of problems or to perform a computation. Well, that definition may not help teachers a lot. Perhaps we could simplify it. An algorithm is a list of rules to follow in order to solve a problem. Well, that's easier to understand, but it's an oversimplification. And simplifications are helpful when teaching. The Rutherford-Ball model of the atom is a useful start when learning how atoms work. But after a while, we realize that it doesn't explain every aspect of how atoms work. So, just giving definitions is problematic. A better approach is to help teachers engage with these concepts head on. So here's an easier way to get across the idea of an algorithm. Instead of splitting hairs over definitions, we can experience an algorithm. Now suppose I want to find out the highest value in a set of numbers. It could be the maximum temperature for the month, it could be the maximum number of products that have been sold, or maybe the high score in a game. What I'm going to do is I have 6 cards here and I'm going to show you one at a time, and my challenge for you is to work out what is the highest value that I show you. So here we go. The first card has the number 2, then the number 6, then the number 5, the number 3, the number 8, and the number 7. So what was the highest value? Well, hopefully you worked out that it was the number 8. But now we can think about this algorithm, the process that you used for solving the problem. For a start, how many values did you have to remember while you were doing your algorithm? Well, probably only one. And how would you define that? The highest score so far, or something like that. So now we've got an understanding of what the algorithm is, and we could of course look at how that algorithm could be implemented as a computer program. But the other thing is that we can analyze the algorithm. How many comparisons of numbers did you have to make? Well, I had 6 cards, but the first one I showed you, you weren't comparing any numbers, so you ended up making 5 comparisons in total. So by doing an algorithm, we gain insight into what it is and what we can do with one. The Unplugged activities generally constrain users to what can be done on computers. So they translate into ideas that work on computers. Of course, it's important not to stop with just Unplugged activities. Students and teachers need to be able to code if they want something to happen on a computer. It's just that using Unplugged as part of the learning seems to get a better result. Unplugged on its own, without programming, is just intriguing puzzles. But coding on its own also risks missing the deep ideas of computing. We've analysed hundreds of thousands of Scratch projects, and it seems that few students post projects that get beyond animations and simple games. Now, that isn't necessarily a bad thing. Young students aren't expected to be implementing complicated algorithms. But it does raise concerns that the approach they've been given to learning programming may not expose them to wider ideas. You can end up with what one teacher called a sprite fest. In contrast, it seems that using Unplugged combined with programming results in students using a wider vocabulary of instructions, as well as developing higher self-efficacy. To take this idea further, we've been developing a plugging it in section for the Unplugged activities that has ideas for linking Unplugged activities to programming exercises. For example, this magic trick, based on error correction, makes it appear that the presenter can read the students' minds and determine which card they flipped over behind her back. In fact, it's just based on counting whether there's an odd number of black cards in a particular row. This program works out if a row has an incorrect number of cards and can reveal which card was flipped. The students have implemented the game that they were just learning about. Students can tackle programming challenges at a range of levels, but the challenges are based on implementing an algorithm that they have just experienced in an unplugged context. We're still evaluating how well it works, but it looks promising. We're also looking at adding more unplugged activities that work in the opposite direction. What are the best physical activities that help students to understand ideas like variables and loops? There are lots of ideas around, but we need to be sure that they don't accidentally reinforce misconceptions. The big challenge when designing unplugged activities is making sure they enforce the kind of restrictions that students will find on computational devices. A variable can store just one value at a time. A decision can compare just two values at a time, and so on. Of course, any pedagogical approach can be delivered badly with little effort, so using a particular resource or method that worked well for one person doesn't necessarily guarantee results for someone else. It needs to be applied thoughtfully to each particular situation. Another valuable way to engage teachers is by integrating computational ideas with other subjects. Maths, and especially geometry, can map well onto programming exercises. Literacy can be exercised with things like pick-a-path stories. The value here is that if a teacher is especially passionate about numeracy or literacy, you're giving them a new tool to help with their favourite subject rather than providing a distraction. Going back to the sorting network, we can integrate musical concepts. A popular variation is to compare musical notation such as note pitches and note lengths. But you can even compare actual pitches. Here are some students comparing the pitches of vowels by working out which one is high and which one is low. And if you want to put integration within integration, you can even get them to write programs for microbits to play a musical pitch, which can then be sorted using a sorting network. I want to spend some time looking at a particular example. One of the popular unplugged activities is showing students how binary numbers work using just some cards. This simple exercise mainly requires the ability to count up to 31, and we can easily show students how using just two symbols can represent numbers, letters, and more. Incidentally, when we do these activities with teachers, we ask them to imagine which answers the students would give to the questions. For example, when revealing the cards for the first time, a child would predict that after the 1 dot and the 2 dot, the next card would have 3 dots. So we ask the teachers, what would a child predict? Now, the 3 turns out to be incorrect, but we support the teacher's mana because they are experts on what the child is likely to say. And this means we're not testing them on their computing knowledge. In this case, 3 is the wrong answer, but when the teacher predicts it, it is the correct wrong answer. Now, taking things a bit further with the cards, students learn that they can represent any number by dots just by saying yes and no. From there, it's a natural step to be able to represent letters of the alphabet, 1 for A, 2 for B, and so on. At this point, we've integrated elements of literacy, letters of the alphabet, and numeracy, adding and subtracting numbers, using the dots as a visual aid. Let's take it a step further and integrate some music. The zeros and ones can be represented with pitches. High notes could be a 1, low notes could be a 0. Now, at the start of this video, I was playing a tune that happens to use this system, so it contained a hidden message. Hiding a message in plain view like this is called steganography, but that's another story. Allow me a small digression to tell you about one of New Zealand's best known computing teachers, who sadly passed away just a couple of weeks ago from cancer. Gerard McManus was a teacher of great mana and greatly appreciated in New Zealand for his work to support teachers to deliver our new computing content in the curriculum. It's been introduced here over the last 10 years. In this picture, he's wearing one of his favourite sweatshirts. Now, the term disobedient teacher is a positive label. It is discussed in a book by Welby Ings. It's not about being difficult or contrary, but about what's best for students, even if the system expects something slightly different. Some teachers are fortunate to have support from administration to take risks. but a disobedient teacher pushes forward despite barriers that the system might impose on them. Now, my wife, Judith Bell, is a music teacher, and she wrote this piece as a tribute to Jared, and we got to play it at his funeral. Jared had a passion for computing and for integrating it with other subjects. To acknowledge this, she coded his name using binary digits and wrote it into the melody using the idea I mentioned earlier. High notes are a 1 and low notes are a 0. If you're into music, in this piece, notes above the middle stave line, concert B, are the dividing line between 0 and 1. Here's how it goes. I've shown the written music, as well as some guidance on the hidden message. As well as being a special tribute, this composition is a demonstration of integrating elements from computational thinking with music in a way that provides a lot to consider in both domains. Maybe if you don't read music, from that demonstration you've now gained some insight into how musical notation works. And if you're a music teacher who doesn't know about data representation, the zeros and ones may now be obvious. In fact, doing this kind of exercise at a teacher event supports the mana of any musicians who are there, because they are needed to help others interpret a binary code. Some of you may recognize this musical representation of binary digits as being the way that bits are modulated to send over a phone line, and demodulated when they're received. That is, we've essentially experienced how a modem works. Rather than define this technical term, the teachers have experienced it in a context that some of them will be passionate about. It's not that they need to know about modems, but they have understood some jargon, which helps their mana, and they have seen another case of how messages can be represented using just 2 symbols. There are so many ways to integrate computing with other subjects, and this can be a great way to get the interest of teachers who are passionate about a particular subject. When you think about it, so much of our life is digital that it's hard to imagine doing much that doesn't involve computing. Sport, entertainment, travel, it all involves computing and digital devices. So, how do we give Manakitanga to teachers? How do we welcome them into this exciting subject and keep them engaged? Well, what do they care about? Their students and things that will help their students succeed. Traditionally, this could be literacy and numeracy so that their students can function well in everyday life. Or perhaps they care about the arts so that students can learn to express themselves. Or maybe it's STEM so that students can have a career in an increasingly technical world. Maybe even keeping things in balance by combining arts and STEM to give us STEAM. Or perhaps it's sport, health and well-being. The thing is that all of these ideas can be connected to computational thinking and computing. In many cases, the lives of both teachers and students have many interactions with digital devices, and we need to recognise that the devices they use to record and share music, to track their fitness, or to communicate with friends are the result of what we know as computation. Not only does this help them to see the value of understanding computing, but it can raise their mana as they see that their existing expertise isn't something disconnected from computing, but a rich source of ideas that can be brought to life using digital devices. Thanks for visiting me in New Zealand, and thanks for caring about computing education. I look forward to catching up with you online, and perhaps when you visit here someday. Ka kite anō.